Okay, section 3.4, subspace and linear independence. Okay, in this section we define a linear combination and spanning set and a linear dependence and the subspace of Rn. Okay, and we will learn how to solve the system of linear equations by using those new concepts. Okay. First, subspace. A non-empty subset of Rn is called a subspace of Rn if the subset W satisfies these two conditions. The first condition is if you choose 2 from W, then vector addition of those 2 is in W. This is closed under the vector addition. If you choose x from a vector from W and multiply a scalar on it, and the result kx and the multiplication of a scalar k on a given vector x is in W, not Rn. It should be in W. Then we call it this is closed under the scalar multiplication. It means it doesn't come out from the W. There is a Rn and there is a subspace, a subset W at W. If you choose 2 out of there and then do the operation, but still does not go out from the W. So it stays in there. That means it's closed in there. Okay. So if it satisfies these two conditions, one is closed under the vector addition and second is closed under the scalar multiplication, then we call this W is a subspace of Rn. Okay. This will make very easy for many computations for you to do. Okay. Okay. First, all subspace of Rn contains 0 vector, because if you multiply 0 on a given vector, then it should be in W. So if W is a subspace, then it should have a 0 vector in it. So if a subset W does not have a 0 vector in it, then we can say it's not a subspace. If it does not have a 0 vector, it cannot be a subspace. Here are some examples of subspace. And the singleton set with 0 vector, it is a subspace of Rn always. And Rn itself is a subspace, because Rn, any vector, if you choose 2 vectors from Rn and do the vector addition, it is still is in the Rn. So it's closed under the vector addition. And if you multiply a scalar on a vector in Rn, then the product of those two is in Rn. So it's closed under the scalar multiplication. So it satisfies two conditions. So it satisfies the condition for the subspace. So these two are always a subspace for a given Rn. Okay. So we call it a trivial subspace. And here is one other example. L0, y equal x in R2, a line passing through the zero origin. Then if you choose any two number from here, it's a y1, x1, y1, and x2, y2, that satisfies these two, then the addition of x1 and x2 satisfies this equation, and scalar multiple of the x1, y1, which is kx1, y1, satisfies kx1 is equal to ky1. So it satisfies two conditions. So it is closed under the vector addition. So a line passing through the origin in R2 is a subspace. But the line which does not pass through the origin, here, the set of this line, set of this point in the R2, is it a subspace? It is not. If you choose a point x1, y1 that satisfies this one, and x2, y2 that satisfies this one, add those two, then what you're going to have is what? 2, not 1. So it does not satisfy it. So, and also, there's the 0 vector, the origin is not in here. 0, 0 does not satisfy this. So this subset is not a vector, a subspace of R2. Okay, here, as you see here, it's okay. So here, as L1 and L2 is in here, this 0, 1 and 0, 2. 0, 1 and 1, 2 is in L1, but the vector addition of those two vectors is not in here. So you see, it's not. So some lines are subspace and some lines are not a subspace of R2. Because it does not, the sum does not pass the origin. All subspace, all line in the R2 does not pass through the origin, is not a subspace of R2. Third, all subspace of R2 are one of the following, only zero subspace. This is subspace. R2 itself is a subspace. And line through the origin. So any line does not pass through the origin cannot be a subspace of R2. Second, in R3, all subspace of R3 are one of the following: zero space, and R3 itself, and these two type. Lines through the origin and planes through the origin. Next, think about. What about? Think about the all subspace of R5 and classify the subspace of all subspace of R5. Can you do that? Subspace of R5. What type will be? That's your homework. Next, show that a subset W. This is a subspace of R6. If you choose two vectors from W and K from the scalar field R, then the vector addition is in the W always, and scalar multiple is in the W always. So it satisfies two conditions. So W is a subspace of R6. Okay. What this space looks like? This looks like, this has only 4 variables. That is almost the same, has the same structure of R4, isn't it? Okay, okay. Next, for A, which is n by n matrix, and show the set of solutions of this linear system of equation is a subspace of Rn, always. We call this W is a solution space or null space of A. Why? Because this W satisfies two conditions. It's closed under the vector addition. This is closed under the scalar multiplication. We have to show that. See, here is the way. To show that, choose two vectors from W and a scalar K from R, and then this X and Y satisfies this. Isn't it? From here, what we have to show is this X plus Y satisfies this, and A times KX satisfies this. These two. Is it true? See, AX plus A times X plus Y can be written as AX plus AY. So AX is 0 and AY is equal to 0. So this is a 0 vector. So this X plus Y satisfies this. This means X plus Y is in the W. And A times Kx can be written in this way, but Ax is equal to 0, so K times 0 vector is a 0 vector, so it satisfies this. That means Kx is a solution of Ax equals 0, so it is in W. So it satisfies these two conditions. So it implies X plus Y is in W and Kx is in W. So it closed under the vector addition and scalar multiplication. So W is a subspace of Rn. It's been proved. That's it. Any question on subspaces? Okay, next example 6 shows, the next is a definition. Linear combination. Actually, you saw this in the earlier chapter 1, in section 1.2. If X can be expressed in a form like this, it's a linear combination of vectors with scalars like this. These xi's are in Rn. Then we call X is a linear combination of vectors x1, x2, and xk's. Okay? If X can be written as in this form with the vectors xi's in Rn, then we call that vector x is a linear combination of a vector xi's. So let x and x2 are given in R3, from R3, then can x is equal to 2 minus 6 be a linear combination of x1 and x2? How can we tell the answer? All we have to do is let x is equal to c1x plus c2x2 and then solve it with this. Solve this. What this means, solve this linear system of equations. Isn't it? Okay, then how are we going to solve? Okay, this is a linear system of equation. You can easily, using the RREF of this augmented matrix, then augmented this looks like this. So what you have is here you have what? You have 0 times C2 is equal to 1. This in this case, the left-hand side should be 0 and right-hand side is 1, which cannot be happened. It occurs a contradiction. So there is no equation that satisfies this. There is no C1, C2 that satisfies this linear system of equation. So there is no answer, no C1, C2. So we cannot, this X cannot be written as a linear combination of these two. That's the conclusion. So answer was no. Next, show that set of all linear combination of S, which is x1, x2, and xk, which is set. We call this so S, which is a subset of Rn. Then all the collection, all the linear combination of those xi's, let it be W. Then this W is a subspace of Rn. This W is a subspace. Here, yeah. So if we are asked to show this W is a subspace of Rn, then all we have to do is using the two-step subspace test. So first thing is we have to show it is closed under the vector addition, and second, we have to show it is closed under the scalar multiplication here. So choose two vectors from W and scalar, and scalar from the rear. Then let okay, then since W is a linear set of linear combinations, so if you choose it, then X can be written as a linear combination of Xi's, and Y can be written as a linear combination of Xi's, like this. So there exist Ci's and Di's. Then addition of those two vectors can be written in this way. Then this vector is a another linear combination of Xi's. So this is in W. Okay. And next, scalar multiple, Kx. Kx can be written in this, since X is like this, Kx can be written in this way. This is another linear combination of Xi's. So Kx is in W as well. So it satisfies two conditions for the two-step subspace test. So W is a subspace of Rn. Okay. Here, particularly the set W is written, it is called as a spanning set. Like here. So we say W is a subspace of Rn spanned by S, which is a set of vectors. And also we call S spans W, and S is a spanning set of W. If we had a subspace W from S, then we call S spans W, and S is a spanning set of W, and W is a subspace of Rn spanned by S. These are all the different the name to explain the situation that we had subspace. And also we write it in this way, W is spanned of S or W is spanned by S. And in particular, if all vectors in Rn can be expressed a linear combination of S, then we should say S spans Rn, which means span of S is same as Rn, which is this. So this can be happened as well. Here, this set S spans R2. And so we can say this S is a spanning set of R2. Or S spans R2. The span of this S is equal to R2. And this S, the set of three vectors like this, or E1, E2, E3. E1, E2, E3, 1, 0, 0, 0, 1, 0, 0, 0, 1. That set is also a spanning set of R3. They spans R3. All the linear combination of E1, E2, E3 is same as R3. So R3 is spanned by E1, E2, E3. And also similarly, R3 can be spanned by these three vectors in R3. Next, column space and row space. Let A be an n by n matrix, then n columns can be written in this way. And n columns spans a subspace of Rn, because n vectors in Rn spans a subspace. Okay? We call that subspace is a column space of A, column space of the given matrix A, and denote by this span of the column vectors, or span of a column space of A, like this. They are same. Similarly, row vectors of A is in the Rn, and that is what? That is and that also spans a subspace. We call it the row space of the given matrix A. So the M rows of A spans a subspace which is a row space of A, which can be written in this way. So if you have a matrix, then we can find the RREF, we can find the column space of A, we can find the row space of A. For these three vectors, then check whether this set of three vectors spans at R3 or not. What are you supposed to do on this? Okay, so here what you have to do is choose an arbitrary vector in R3, which is X, and show whether it can be written as a linear combination of these given three vectors. So let's form a, let's rewrite this condition that we're going to show in a matrix form like this. AX is equal to B like this. Then solve this linear system of equation. Okay? But in order to do, just to try to find the RREF of this matrix, then we know this has what? 0 row here. But as you see, any linear combination of this will make some x, y, the linear combination of x, y, z in here, which is not always 0. So left-hand side is 0, and right-hand side may not be 0. So it does not has any solution. So what this means, what this linear system of equation means is one of CI's may not be determined. So the linear system has a case that the system cannot determine a unique solution, which means, some vectors in R3 cannot be written as a linear combination of this C at Xi's. So that does not span R3. Next, linear independence and linear dependence. This concept is the terminology that we are introducing to explain the situation that you had seen in the earlier examples. Here, S is a subset in Rn, and then if the linear combination of this is equal to 0 implies all the coefficients Ci's are equal to 0, then we call these vectors, or the subset S is linearly independent. If not, then we call this set S is linearly dependent. This is a new concept, linearly independent, if not linearly dependent. Linearly independent, you have to show this. Linear combination of those given vectors equal to 0 should imply all the coefficients should be 0 altogether. So, if S is a linear dependent, what this means is that there exists at least one non-zero scalar in CI such that the linear combination of those is equal to 0. So this is extra information for the to explain the linear dependent. Yeah, we defined the unit vectors in R3 and we expand it to the Rn. E1, E2, En. These are called the unit vector of Rn, and also they are linearly independent because if you make a linear combination of those as equal to 0, then you will see this hold, which means C1 is equal to 0, C2 is equal to 0, and Cn is equal to 0. This should be Cn. 표시 좀 노트 좀 해서 줘라. Okay. This should be Cn. Cn should be 0. Okay. So if x1, x2, x3 in Rn are linearly independent, then these are also linear independent. How? The linear combination of the linear combination of those three vectors is equal to 0, then this implies this. In order to solve this equation, then what this means? Since x1, x2, x3 are linearly independent, yeah, we can say all three coefficients are 0. So we solve this linear system of equations of CIs, which means which gives us C3 is equal to 0, which that means C2 should be 0, and C2, C3 is equal to 0, that means C1 should be 0. So C1, C2, C3 should be all zeros, which means these three vector x1 and x1 plus x2 and x1 plus x2 plus x3 are linearly independent. And here is another three vectors. Show these three vectors are linearly independent. Linearly dependent, because let the linear combination equal to 0, then form a linear system of equation. Then as you see here, this vector has 0 rows like this, which means it has no it does not have a unique solution, and the sum C1, C2, C3 can be 0, or it may not be 0 to have this condition satisfied, which means these are not linearly independent. That is, S is linearly dependent. Okay. Okay, here for a set S in Rn, the following hold. And the set S in Rn and the subset S prime of S hold the followings. First, a set S is linearly dependent if and only if some element in S can be expressed as a linear combination of the other element in S. That's one. The second, if S contains a zero vector, then S is linearly dependent. If a subset S prime of S is linearly dependent, then S should be linearly dependent. If S is linearly independent, then S prime is also linearly independent. These are the four important properties. Okay, we show the first part of it. S is linearly dependent. Then that means there exists some CIs that satisfies this, and at least one element in CI is non-zero. So let's say, without generality, without loss of generality, C1 is the one which is not 0. Then we can divide all this by C1 and move the other terms except x1 to the right. Then x1 can be written in this way, which means x1 can be written as a linear combination of the other vectors, like what is said. Some element in S can be written as expressed of the other vectors linear combination. Like so it's been proved in the other direction. Suppose we can write this as a as a linear combination of x1 is a linear combination of other vectors in S, then we can rewrite it in this way, which means sum of the linear combination is not, the linear coefficient is not 0 that satisfies this equation, because the first one was not 0. So S should be a linear dependent. So this if and only if statement can be proved in this way. Others can be shown in the similar ways. Next, this is the last theorem in section 3.4. In alpha n, if m is bigger than n, then those set of m, the vectors of m vectors, a set of m vectors are in Rn are always linearly dependent. If you have Rn, if you have a many number, which is more than n vectors in it, then that subset is always linearly dependent. So maximal linear independent set can be n. So if you have n Rn, then if you have a subset, linear independent subset in Rn, then the number of elements should be not more than n. Not more than n. That's what it means. Suppose if you were asked to show whether these four vectors, the set of these four vectors in R3 is linear independent or not, then you don't have nothing. Because in R3, if you have four vectors, then it cannot be linear independent. So you can say it's just linearly dependent. Always. That's what it says. Okay. Lines and plane. Okay. From the viewpoint of subspace. The span of non-zero vector in V, which can be in this way. This is a subspace containing the zero vector. Also, this set of vectors form a line through x0 and parallel to V. In other words, this line is a translation of the line, and that passes through x0. But in general, if these are the vectors in Rn, then x can be, and then this x, the linear combination of these vectors, x is a subset of Rn, which is a translation of a subspace, which is this, through the origin by x0. So this is what this means. This is a kind of plane which is spanned by these V1, the set of vectors V1 and up to Vk. So this is a subspace. Then the set of these vectors are a translation of this subspace. Okay. I think that's it. This concept will be used to solve when you try to find the set of all solutions of the non-homogeneous system of linear equations. Any questions?